Hello students, in this video we'll prove a vector identity for a component of the convective derivative that's seen in the Navier-Stokes equations. In particular, we'll be interested in showing that the directional derivative in the direction of a vector field v of the vector field v itself is 1/2 the gradient of the normal v squared minus the vector field curled with the curl of the vector field. The cross product of v with the curl of the vector field. So let's prove this. So let's look over here on the right hand side. So if we have that first term, 1/2 the gradient of v dot v is going to be 1/2. Well, the gradient is what? The gradient is going to be the sum of partial xi delta I hat, the sum over I. And then this v dot v is going to be the sum over j of vj squared. And so what we see is when we do the xi derivative of this, the 1/2 is going to cancel out, and we're just going to have a factor of what? We're going to have the sum over I and j, the sum over I and j of a partial vj, so I'll have a vj times partial vj partial xi in the direction of xi. So that's what that first expression gives over there, something relatively simple. Now what we want to do is we want to carefully examine this term over here and see what we're going to get. So let's take a look at that term over there. So we're going to have v cross with the curl of v. Okay. And so let's remember what the curl of v is. So this is going to be what? This is going to be the sum over I, and then the sum of what? Of vi delta I hat. And we're going to cross this with what? With the curl of v. And what's the curl of v? It's the sum over r, s, and t of partial v, partial vs, partial xr, epsilon r, s, t, and then a delta t hat. And so now these terms over here, I'm going to sum over I, R, and S, and then I'm going to have and I need a new variable over here, so I'm going to sum over I, R, S, T, and let's say K. Then we'll have a VI partial, VS partial XR. Then we'll have an epsilon RST. And then when I cross delta I and delta t, I'm going to get an epsilon I t and then k delta k hat. Excellent. Now what we're going to do is we're going to use match-mismatch. So match-mismatch is going to involve these two terms over here, but I need to see the t in the second slot. So what we have over here, our expression over here, the sum over what? The sum over t of epsilon RST, and I'm going to put the t in the second slot, so I'm going to put a minus sign over here so I can flip those two indices. Epsilon I kt by flipping two of them. By match-mismatch is going to be negative delta ri delta sk minus delta rk delta si. So if I flip the sign, this is going to become delta is delta rk minus delta ir delta ks. So let's simplify that. So we're going to have the sum. Now I can eliminate this sum over k now. Let's go back to our original series over here for the second term. So the second term is going to be the sum over 4 indices over irst, irs, and t of vi, then partial vs, partial xr. And then we're going to have a plug in our match-mismatch. So delta is, delta rk, minus delta ir, and then delta sk or ks, and that's in the direction of delta k. So I don't have t anymore. I have a k, so there's a k there. So I summed over t, so there's going to be a k still, so delta k hat. So k sticks around. Good. All right, excellent. And so now let's look at each of these two terms. So I have two terms that arise from this. Let's look at the first term over here. So in this first term, I'm going to replace all the s's with i's and all the, let's do all the r's with k. So that we're going to have the sum over I and the sum over k of VI, that's good. And then partial VS, well, what's S going to be? We know that S is going to be I, so it's a partial VI. And then a partial XR, but R gets replaced with what? R gets replaced with K, so that's partial XK. And that's going to be in the direction of delta K hat. That's the first term over here. Then we're going to have minus what? Minus the sum. I'm going to do I and K again. I and K. I and K of what? Now, my I's turn into R, or my R's turn into I rather, so I'm going to have a VI again. That's great. And then I have a partial VS, but S turns into K, so that's going to be partial VK. And then what? It's partial VK, and then R turns into I, partial XI. Partial xi, and that's in the direction of delta k hat. Excellent. Now over here what we can do is we can rearrange these things a little bit, and we can notice that our expression over here, so these two expressions, 1/2 v, 1/2 the gradients rather, gradients of v dot v minus v cross what? Cross the curl of v is going to be equal to, I'm going to take all these i's and just turn them into k's instead of k's over here. So those terms over here, if I just turn these i's into k's, it won't change anything, is going to be the sum over j and k. The sum over j and k of what? Of vj, partial vj, partial xk, and then delta k hat. And I'm going to subtract off this first term over here, so it's going to be minus the sum. I'm going to turn those i's into j's, so that won't change anything either. So the sum over j and k of vj, partial xk, and then delta k hat. And then that's going to turn to a plus the sum over j and k of vj, partial vk, partial what? Partial xj, delta k hat. Excellent. Now we see that these first two terms exactly just cancel out, and what we're left with is that last term over there. So this is equal to the sum over j and k of vj, and then partial vk, partial xj, delta k hat. Well, this is exactly what? That's the directional derivative in the direction of v of what vector? Of the vector v. So this expression over here is exactly equal to, by definition, this is equal to v, the directional derivative in the direction of v, of the vector field v itself. And therefore we have our identity that the directional derivative in the direction of v of the vector field v itself is 1/2 the gradient of the norm of v squared, v dot v, minus v cross the curl of v. Thank you very much.